Hey, so just started off with Amazon SageMaker, and this is going to be more Python based. Most of the other lessons we talk about are, doing predictive modeling, machine learning, and that's really what this is. I'm seeing that it started off with the fundamentals of generative AI. Hopefully I'll be able to go through a couple real examples and dive into the data. So, welcome to your SageMaker Studio lab. It's got a CPU and a GPU. Noise. And I'm sure you all know, when you're in Jupyter, you can change, hit escape to bring up the menu, and then you can go to, if you hit escape and then M, it changes it to markdown. Then you hit control enter to execute. You can run chunks as code or as text. But yeah, SageMaker distribution images. Now supports SageMaker distribution images, which provide richer set of libraries that aren't present in the default environment. Also provide consistency with environments with Amazon SageMaker Studio. Notebooks as the default environment. This kind of makes you wonder, are notebooks really the best way to be running and organizing all of your code? Because when I'm building an application, for example, or I'm running things in bash command line, running entire notebooks, they can't be executed quickly. So while there are a lot of advantages to using Jupyter, there's also some things that it can't do well. Okay, so they do have a console. We all know how to install packages. AWS Machine Learning University. You can clone their notebooks. That's pretty sick. Accelerated tabular data class. Okay. So who are all these folks that created this? What happened to their research? Is this they just got published? Or do they just become part of the corporate machine? Okay. Here's Introduction to ML, Model Evaluation, EDA, Feature Engineering, Tree-Based Models, AI ML Services, Neural Networks. Because what I want to see is something called predictive intelligence. Predictive analytics is when you look ahead and you make forecasts about what will happen. But it also just includes things like getting insights or importance as to which indicators lead to certain outcomes. It doesn't necessarily have to be future, but getting a little off topic. Huh. I So it looks like they had this thing before that was just focused on machine learning. And now this is more just like general. I'm just getting a little bit lost here. I want to go back to the page where it showed all of the, not the machine learning university thing. I guess it was this one. But then when I clicked on the sidebar, dive into deep learning. Let's look at clone Hugging Face notebooks. Hugging Face is the platform that allows you to use data sets and also models. Here's an auto ML. It's like what, an ensemble method? Tabular data. You notice that this data set, the Austin Animal Shelter data set, is one from the exam PA in like June of 2022. I just made that connection of that's probably why they use this data set. It's funny because I lived in Austin though. Okay, what is this? What type is it? Type. This isn't running. It's not giving me anything. Test data dot head. Okay, I guess this isn't actually running. It says it's connected to the kernel, but it's not actually running. That's unfortunate. So I can't actually run this notebook. Well, what's the point of doing this then? I just want to see. Maybe I have to stop the runtime and then restart it. All right, now I'm going to start. Yeah, the thing that just kind of makes me pause about like something like this is that it's almost like too, like, it's set up in such a way that it's hard to make a lot of changes to it. Where, let's say you just have a studio, on a on your own virtual desktop running Anaconda, and you have like Visual Studio Code, and you're just able to run the code in whatever order you want. It's almost a faster way to learn about something, and then you just like create your own test predictions and then submit them to a Kaggle competition and see how you rank on the leaderboard. That's like the simpler way that I learned how to use machine learning, was by doing like Kaggle competitions, and instead of like following all of these online courses. And I guess now it's more like it's probably faster to learn everything now because we've had more discoveries, more advancements in the field. Okay, this is just not loading. Clear workspace. I thought this was going to teach me about Gen AI, not just machine learning. So you have introduction, preliminaries, linear neural networks, multi-layer perceptrons, optimization algorithms. Well, yes, computational performance, computer vision, natural language processing, attention mechanisms and transformers, modern recurrent neural networks are a type of, well, transformers are a type of modern recurrent neural network. I would say that though 15, this natural language processing can exist outside of, neural networks. Like you can do um, like simple parsing and similarity measures and ways of comparing textual similarity and finding things that just using like machine learning. You don't necessarily need to have deep learning, though. This isn't also generative, of course. There's nothing in here that says this is generating, like generating data with a. So it's an introduction, and then it goes from preliminaries, EDA, calculus, probability, linear neural networks, regression, then multi-layer perceptrons, multi-layer implementation, numerical scalability, and then part 2 is modern deep learning techniques. Deep learning computation, convolutional neural networks, modern convolutional networks, recurrent neural networks, modern recurrent neural networks, attention mechanisms, scalability, optimization, gradient descent. I feel like gradient descent should be a lot earlier on because that's like fundamental. I mean, you use gradient descent on logistic regression, for example. Um, this looks good though. Natural language processing. And then the last topic is fine tuning. They don't talk about pre-training or transfer learning. Yeah, transfer learning is so huge. I can't believe they don't. Oh, they do neural style transfer. There we go. How do I click there? Do I? Huh? What did I do? I broke this thing. Oh. Okay. Oh, because it's doing like search. When it does the control search, it's searching through like everything. Ah, that's frustrating. But okay. So each of these are separate notebooks. Cool. So there's maximum likelihood, probability of parameters given the data, the argument max of probability of x given theta. This is just Bayes' rule. Probability of theta over probability of x. Fine tuning. Layer, source dataset, target dataset, random initialization, target model, train from scratch, fine tune. Hot dog recognition. I remember this one. This term is a hot dog recognition. I think this was on Kaggle sometime. Or maybe it was on the deeplearning.ai website, this hot dog thing. Hot dog or not a hot dog? Actually, there's something else. If you look for think one of my videos talks about machine learning credibility theory. It's almost like fine-tuning. You can actually see the notebook that I have below the video. And what I'm basically saying is that it doesn't matter if you're using like a neural network or you're using a neural network, or in this case it was XGBoost. Come on. You can actually download the RMD file if you want. Machine learning by looking at examples, and supervised learning is known as an outcome or a label. Many examples are made, and a relationship is found between the data and the target. Having more examples makes it easier for the model to find patterns. Having fewer examples makes it difficult to learn. So, like, this was on the mushroom data set, and it just used XGBoost. And you first created, like, let's say you already had a model right here, and this was the so those are the so like here, so I trained a model right here, xgboost.train parameters, and then I made the prediction, right? It's like 49%, 48%, and then I retrained it, or did continuous training. Continued training is also what it's called, or fine tuning. And then you get to, a higher percentage. It's like 100%. 100%. So it goes from 74% up to 100%, and from 49% to 48%. So it's a way to do this just like this is doing, fine-tuning. Transfer learning transfers knowledge from learning the source dataset to the target dataset. Fine-tuning is a common technique for transfer learning. The target model copies all model designs with their parameters from the source model except the outcome layer. The fine-tunes these parameters based on the target dataset. In contrast, the output layer of the target model needs to be trained from scratch. Here's RNNs, tabular and image data. This is just the index. I want to see the language models and data set. We see how to map text data into tokens, where these tokens can be viewed as a sequence of discrete observations, such as words or characters. Assume that the tokens in a text sequence T, x to 1 to T, then the sequence can be considered as observations or a label at time step T. Given such a text sequence, the goal of a language model is to estimate the joint probability of the sequence. The probability of all of those things happening at once. Language models are incredibly useful. The obvious question we hold, the probability of x1, well, we assume that it's the product of all of the probabilities conditioned on the other probabilities. So probability deep learning is fun. Its probability of deep learning given deep times the probability is deep in learning, etc., etc. probability of learning deep, they're just using Bayes' rule and deep learning. Right. Um, how do I run all above? I guess I just have to run all of them. Um, so it's like, to begin with, since the set text sequence can be arbitrarily long, such as the entire machine learning book, we can partition such a long sequence into subsequences with the same number of steps. When training our neural network, a min batch of such subqueries will be fed into the model. Suppose that the network processes a sequence of n steps at a time. Figure 813 shows the different ways that obtain sequences from an original text sequence where n is 5. And a token at each time corresponds to a character. Note that we have quite some freedom since we could pick an arbitrary offset that indicates an initial position. Random sampling. Define sequence data iteration random, corpus, batch size, number of steps. Generate a min batch using random sampling. Data position num batches over batch size. For I in each of the batch sizes, you have initial indices contain randomized sampling for subqueries, and then initial indices per batch. Sequential partitioning. Have you heard of the partitioning problem? Is really difficult. Like, how many different ways are there of partitioning like a given number? But So they're using max tokens of 10,000. And like you look at like some of the new like GPT, how many tokens did Chat GPT-4 use? It's trillions. Oh, I'm sorry, 8,000 token limit in another 32,000. It allows for 1,024 tokens to be sent in as input. So token counter. So there's like apps that will do this. But anyways, this is all kind of interesting. This is all very good. This is like really, really good reading. Like it's well written. Well, hopefully, some of that was like useful. Some of the stuff that that maybe I'm learning or relearning, maybe you are also learning at the same time, and it's a way to just have more connection about putting together the pieces for predictive analytics, also like deep learning, natural language processing. I feel like those are really powerful combinations because we have like chatbots and we have generative AI. And then if we have the ability to predict things that are going to happen in the future, just think about the vast amount of data that's currently available. And then we could use that to like make predictions about what's likely to happen. Like, all this stuff about feature generation and auto ML. It's using like unsupervised and clustering and k-nearest neighbor to like create features on the fly. Well, like ChatGPT, for example, or Minstrel or Llama 3, like what if we use those for the feature engineering processes and then we like took that input, but you have to get into the problem of, oh well, if we create features using those, they're going to be very unstable over time because just look at how frequently the models change. You had ChatGPT 3.5, GPT-4 Turbo, GPT-4 Omni. What's going to be once we're going to have GPT-5, right? So if you used those models in your data set, then it would become moot, like unstable over time. So that's when you have to really go back to like the core principles of the probability. And so you have to like, you know, break down what you're doing, document it in basic math and algorithms. Um, I mean, like take like XGBoost for example. XGBoost is like, well, take like a simple neural network. You first create like an initial set of parameters, and then use gradient descent, use back propagation to find the sequence of weights that best results in the target outcome to minimize the gradient um, of the loss function. Well, there's so many like questions like when you create the training and testing split, you're not supposed to look at the data that's in the test set when you choose the any of the parameters in the model, or when you make the choice of the type of model that you want to use. You're supposed to put the test set away in a box and lock it. And then that's how you evaluate if the model is effective or not. Because if you kind of break those things down, like if you start using supervised learning for feature engineering and you use the supervised learning features in the test data set, that's technically cheating. And so when you try to apply that into real life, what you'll find is that on new data, the performance will be garbage because you haven't really found patterns. What you've done is just overfit to the sample. Those types of things are really hard for like non-data science, for people that don't have a background in data science, that just sort of cheat their way through. Like if you just ask ChatGPT to do that, for example, I don't think ChatGPT would have the forethought to like go through all those processes to make sure that you're using correct uh, that you're using the correct methodology. Like so yeah, it's really interesting. Also, the stuff about language modeling, what I was reading about tokenization and how complicated language is. Like if you have a string of, 100 characters, you can divide that up. Like you could just go, okay, I'm going to divide it up into 5 equal parts of 20 characters. Or you could just look at the first 50 characters and then look at the remaining 50, in small chunks of 10. Like there's so many ways of partitioning out the word, and then you can look at the co-occurrences, the probability. It's like, oh, if you have the word dark, there's a high probability you'll have the word thunderstorm. If you have beach, you'll have sunny. And then you can also get like similarities, like king is to queen as rook is to knight based on the co-occurrences of the words. So if you that's like um, it kind of breaks down the way that we think about language. And I guess the other thing about language is that you use recurrent neural networks because there's a time component, right? It's a sequence that you start at one point and then it ends at another point. It's not like a random string of, like, if you have a deck of cards, you're dealt a hand of cards in poker, you know, and those can be like in any order. There's no order. There's no time component to that data. But when you work with speech, there's a sequence that naturally evolves. And so when you look at your data set, if you lose track of the time variable, that creates a lot of confusion. And um, yeah, there's so many like things that are really hard to communicate to like your models when you're building your models. And I don't know, I find it really fascinating. Hope that you all do too. Bye. Have a good one, I guess, wherever you're watching this from. Um, yeah, it's really just an interesting. I hope that you have a good time if you're working. Maybe you're working in data analysis, or you get to play around with Jupyter notebooks. If you do get to use like powerful GPUs with image models or maybe video, that's awesome. That's awesome. Keep it up. You're helping to make scientific progress happen.